Hello, everyone. My name is Oscar Ferrero, and I'm here with my teammates Ralph Cunningham and Mashoud Kabur, and we're gonna talk. We're gonna go over today our energy conversions class project, which is a solar energy application for a retirement housing. So this is our outline of the project. The outline represents the topics that we're gonna be talking about. We're gonna start with our motivation and objective, a little bit of background, and then we're gonna finish with our cost analysis and conclusion of the project. So the motivation. The motivation of this project was to provide the audience the economic and environmental reasons to switch or not from a natural gas system to a solar energy system. The objective. So the objective of the project was to create an engineering model of a solar energy system in Simulink, then perform a cost analysis of the solar energy system and compare it to a regular natural gas system. So natural gas background. So how do we compare natural gas into electricity? So there are two ways of converting natural gas into electricity. The first way is through an open cycle. In this cycle, natural gas is burned to produce pressurized gas, which is spins the blades of a turbine connected to a generator. Inside of the generator, magnets spin, causing the electrons in wires to move, creating an electrical current, which generates electricity. The second way is with the combined cycle. The combined cycle uses the waste heat to boil water and produces steam which drives a second turbine, generating even more electricity. This means that the combined cycle power plants are generally more efficient than open cycle ones because it generates around 50% more of electricity. Natural gas power production. So the usage. Natural gas power plants supply 52% of the state's electricity net generation, which is about 238,000 gigawatt hour. The price per kilowatt hour of capacity ranges from $820 to $2,080 depending on the method used. Emission rates given in pounds over megawatt hour are for carbon dioxide 1,135, nitrogen oxide 1.7, and sulfur dioxide 0.1. Solar energy background. So when the sunlight hits the top silicon layer, which we can see here is the N-type silicon, it excites the electron and gives them enough energy to move. The electrons begin to flow from the top to the bottom layer, which is the P-type silicon layer. And as we know, when a bunch of electrons start moving in the same direction, this generates electricity. Then the electricity will be going through the house. But first, this electricity that the solar panel is producing is DC current. Is DC, which is direct current. And our house needs AC, which is alternating current. So then this electricity that is DC needs to go through an inverter. And the inverter converts the DC electricity to AC electricity. So solar energy usage. So can solar energy power your entire home? Yes, it can actually power your entire home, and it can actually produce even more electricity than your home actually needs. When this happens, the extra electricity produced by your solar system can be sold to the utility company, and then the extra electricity will be sent to the power grid. So the future of the solar energy industry. In the future, the price of the solar energy systems are predicted to decrease in price, which will increase the amount of solar energy projects around the US. These cost decreases are anticipated to increase the power produced by at least 700% by 2050. So now we're going to talk about the policies on solar energy. The first one that we have here is the Federal Investment Tax Credit, ITC. The ITC is a 30% tax credit for solar systems on residential and commercial properties. The second one is the Modified Accelerated Cost Recovery System, MACRS. The MACRS is a method of depreciation in which a business investment in certain tangible property are recovered. for tax purposes over a specific time period through annual deductions. The next one is the Public Utilities Regulatory Act, PURPA. The PURPA requires utilities to buy power from independent companies that could produce power for less than what it would have cost for the utility to generate this power. This is called the avoided cost. The last one is the Federal Energy Regulatory Commission, which is an independent agency that regulates the interstate transmission of electricity, natural gas, and oil. FERC or FERC also reviews proposals to build liquefied natural gas and interstate natural gas pipelines, as well as licensing hydropower projects.
All right, so the methodology and simulation of our system that we have here for our 8 kilowatt system for our retirement home community. I first want to say thanks to MatLab and Simulink's on-ramp training certification program. That was very insightful and very helpful for developing this power grid. I'm going to start from left to right and explain how the system works and dive into the details later in the later slides. So the power grid is been generated for not just for this community, but for the whole town. That's what the pole-mounted transformer is for. Pole-mounted transformer is able to produce take away what energy and electricity needed for this community alone, and it will send it to the community that is needed. We were able to use the microgrid examples that Simulink has provided us to help give us a good starting point for our power grid and pole-mounted transformer layout. So thank you to that example and their power. To dive into our community, the pole-mounted transformer shows that it actually delivers the electricity it's needed for this community towards the solar panel first. The electricity goes to the solar panel to be able to operate the solar panel's inverter and to be able to go from DC to AC and to help also transform energy from the solar energy into electricity. So the solar panels also operating basically within an 11-hour study. And we also took in effect on partial shading with clouds and everything. So we also used the microgrid example to help with that as well for a good starting. We have 32 panels for our solar system to help produce for 8 kilowatts for the whole community. And the cool thing about solar panels is that it's a two-way system. So the solar panels that generate enough electricity will actually shoot back the amount of electricity needed to the houses, and the extra will go back to the power grid, where the power grid company will actually reimburse that home for paying back the electricity. So the next step is then the battery. The battery will be able to store the amount of power that the solar panel is able to generate to whenever there is no sunlight for the solar panel to help power up the houses. The battery will take charge and take on the role of the solar panel and help power up the houses for the rest of the night. And then each house is on the same amount of load system that was generated, and house 4 at the very end actually has a main breaker switch because it is the last house in the system. Whenever that house has reached its operating electricity power, the main breaker will switch back to the rest of the electricity needed to the power grid. So there's no excess waste of electricity. So this is our loads that are for each house and for our photovoltaic cells in our solar panel system. We were able to have a good load data and solar data due to the lookup tables developed by Simulink. We use these lookup tables to help generate all specified loads for each house and the photovoltaic properties that are needed to generate the outcome for each house. And for the scopes were also helped generated through the microgrid example. They had a great starting point. Each scope will produce the power developed by the photovoltaic cells. Then there's the power load that was generated for all the loads on the houses, and then the power battery that was stored up throughout the night and when it turns on to produce the amount of power needed. Remember, this is on an 11-hour cycle, but it's on a 24-hour cycle as well. So when you see the graphs, it's on 24-hour scale, and this is what I'll explain. So on the very bottom graph, you could see the hours, and it's on 24 hours of showing when the day is. So that's what the increments are showing, what it's doing. So at about around 7 a.m., you could see that the power for the photovoltaic cells are starting to heat up and start actually producing power. That's because the sun is rising around 7 a.m. And then it just keeps incrementally getting higher and higher and higher until around probably, I want to say like around 4 p.m., 5 p.m. That's when the max peak is starting to slowly dip down. And you can also see when it starts to slowly dip down, the power battery actually starts to pick up a little bit right when it's starting to get to its lowest point. And the power battery starts to shoot up and take over for the rest of the night. And you can also see for the power battery that the power battery actually starts working in the morning as well. And when the people are sleeping, the battery doesn't really need to work as much because the house is at minimal power needed. But you can see that its power is not at zero. It's at a increment that's a little higher than zero to help supply for just normal early morning 2 a.m. power needed for the house to be able to keep it afloat. But these are all our scopes that were presented from our simulation, and it all makes sense and are accurate for us for our cost analysis.
We will be conducting a cost analysis to compare the two systems and see which one is more beneficial. This is the problem statement for the system we're trying to go with, the solar system. A solar energy system wants to be installed to replace the natural gas energy system for a retiring home complex of 4 houses. The system is 8 kilowatt hour total with an installation cost of $7,500. Maintenance cost for the solar panels is around $1,200 per year. And the cost for solar energy is around 5 cents per kilowatt hour, and for the natural gas is around 12 cents per kilowatt hour. The interest rate given by the investors is around 5%. And we have considered a period of analysis of 10 years. Is the solar energy system a good investment? Let's find out through our cost analysis. These are assumptions we have considered that are really important. So the system is in steady state. We have a solar irradiation of 3.52 kilowatt hour per meter squared per day. This is obtained from the zip code of 77057. We have 0 kinetic and potential energy. And the average amount of daylight is around 11 hours, and 32 solar panels total are used for the system. LCOE stands for levelized cost of energy. And for the solar system, based on our calculation, we have gotten $32 per megawatt hour. And for the natural gas, it's around 36.61 megawatt hour. And this value is obtained from the EIA data. EIA stands for Energy Information Agency. These are more values we got for the system. These are cash flow values. The NPV for the solar system, the net present value is around minus $5,250. The EUAC, which stands for equivalent uniform annual cost, is around minus $4,500. The annual cost is around $3,700, and the payback period we have that is less than 4 years. And then ROI, return on investment of 59.9%, which is pretty great. This is a comparative table between the two systems, the solar system and the natural gas system. On the first column, we have the initial cost. The initial costs include the installation costs and the cost for equipment, for buying the equipment. For the solar system, we have $7,500, and for natural gas, we have $28,000. The salvage value after 10 years, salvage value is the value accounting, the value of the equipment of the installation, accounting for the depreciation rate. It's around, using a percentage of 16, it's around $1,300 for the solar system and $4,900 for almost $5,000 for the natural gas, and preventive and maintenance costs $1,200 for the solar energy system and $67 for the natural gas system. Obviously, the solar energy system doesn't require energy for functioning. And for natural gas, the cost for fuel is around $296. From the analysis, it came down to a annual saving of more than $2,000 for the solar energy and more than $1,000 for the natural gas. So the solar energy is pretty beneficial. Conclusion. The solar energy is a pretty great energy system. It's harmless for the environment, while the natural gas is not. While natural gas is more efficient than solar energy, it's a viable option as a renewable source of energy. And the solar energy system is something very promising for the future, given the numbers above, around 700% of increase for the upcoming years. These are the references, more reference, and these references include websites, books, articles, and journals. More references. Thank you for your valuable time. This concludes our presentations. The following slides are for appendices. We have the calculations one, more calculation appendix, using MatLab. And this is the solar irradiation. The Gantt chart showing the timeline and the different milestones we had hit. Second part of the Gantt chart. This is a checklist showing that we've checked everything and everything is green.